Hi everyone, I hope you're doing well. I figured maybe we'd start this one with a do now like we typically do. That spirals backwards. So why don't you pause the video here, try these two problems, and then I'll go over them with you. Okay, so for the first one, we have log base 2 of 5 equals x. You could just use the log base key in your calculator. And remember, you would hit the math button and scroll down to A. It should set up the boxes for you, and log base 2 of 5 is approximately 2.3219. Okay, for the second one, we have f of g of x, so a composition of functions. And after you do that composition, you should end up with h of x, and the h of x should be this. So they're saying, what is a possible f of x and g of x that we could use? So there's multiple answers here. Let's just do what I think might be the most common for you guys. Remember, this is going to happen first. So you first want to start by saying, what should g of x be? What's the thing that I am going to start with that would be my plug-in piece? And a good idea here would be a 2x. Now remember, after you have that g of x, you walk over with that and you walk over to f of x. And anywhere there is an x, you are going to try to substitute the 2x instead. So we have sine, we have a squared, and wherever we want that 2x to go, we're going to put an x in place. So this is probably the most common answer for this question. So last week you looked at circles and you looked at ellipses. Now we're going to talk about hyperbolas. Your standard form for a hyperbola is ax squared minus by squared equals r. It's going to be handled a lot like the ellipse, but it's going to look very different. So in this case, you have an x squared and you have a y squared, but your coefficient on the x squared or your coefficient on the y squared has to be a negative. And if that happens, then you end up with your hyperbola. If your x squared is the negative, then you will have no x-intercepts, and so your hyperbola will look like the picture that we have here. If your y squared is the negative piece, then you have no y-intercepts, and your hyperbola will look like a picture here. So when you guys have an ellipse, the plus makes these loops want to come together. When you have a hyperbola, the minus makes those little half loops push apart from each other. Okay, so let's look at an example. X squared minus 4y squared equals 16. We have an x squared and we have a y squared and we have a minus. So we know this is going to be a hyperbola. We're going to do the same thing with this that we did with the ellipses, and we're going to try to get everything to equal 1 over here. So that means we're going to divide everything by 16. So we divide. So if we break these pieces up, we have x squared over 16 minus 4y squared over 16 equals 16 over 16. When you simplify, the x squared over 16 stays that way, but the 4 goes into itself once. Sorry, I forgot my squared on this way. The 4 goes into itself once, it goes into the 16 4 times, and then the 16 over 16 is a 1. So now we are here. You're still going to handle this the same way as an ellipse, and then we're going to just modify it a little bit. Based on the ellipse, if I said to you guys, what are your x-intercepts? You would look at this bottom number and square root it, and so you would say plus or minus 4. If I said, what are your y-intercepts? You would look at that 4, square root it, and you would say plus or minus 2. But because there is a negative in front of the y squared, we actually have no y-intercepts. Keep that in mind as we go to the next page to graph. Okay, so when we graph now, if you guys are looking up here at the corner, this is just the previous screen, so I had it to look at. You had those x-intercepts of positive and negative 4. So I have these two spots right here. Even though we don't have y-intercepts, I'm still going to mark up a 2 and a negative 2 on my graph paper. Then what's going to happen, you're going to go ahead and draw a rectangle to connect all of those dots. So if I do that, you see what I have going on out here that I'm doing in yellow. It's really important to keep this dotted. anything that's a solid line is considered a part of your graph. Anything that's dotted is not considered a part of your graph. And what we're doing here is we're just creating a framework to help us draw our hyperbola. Okay, so now we're on step 2. We're going to draw diagonals from one corner to the other of the rectangle. Mine are a little bit off just because I was trying to use the iPad, but yours should be really good. So I'm going to go from one corner of the rectangle to the other. And again, we're making it dotted. Okay, and you want to extend out. So that's what I have here so far. Okay, now we're up to step 3. It says draw the hyperbola based on which intercepts actually exist and use the diagonals as guidelines. Now, when we looked at it, we said the x-intercepts exist. Those are a 4 and a -4. The y-intercepts actually don't. So we're going to go ahead and keep our 4 and -4 as intercepts on the x-axis, and we're going to go ahead and sketch using these diagonals as a guide for asymptotes. So it comes out over here, and on the left side, it looks something like that. And remember not to cross over those asymptotes. Okay, let's try another example. So 25y squared minus 4x squared equals 100. We have an x squared, we have a y squared, and we have a negative, so we know it's a hyperbola. Please note that the y squared is first here and the x squared is second. If you want to leave it like that, it's fine. If you're afraid that you might mess it up, it's not a bad idea to go ahead and rewrite it with the x squared first and the y squared second. But standard form, they're probably going to put the negative in the middle. So we want this to equal a 1, so we're going to divide every term by 100. Now we're going to reduce. So 4 goes into 100 25 times, 25 goes into 100 4 times, and 100 over 100 is 1. So our new equation looks like negative x squared over 25 plus y squared over 4 equals 1. Now, if I was thinking about x and y, I would say, okay, my center is still at 0, 0 because nothing shifted here. So my x-intercepts are positive and -5. My y-intercepts are positive and -2, but because the x squared was negative, we have no x-intercepts. But to graph, we still want to consider them. So on the x-axis, I'm going to go out 5 to the right, 5 to the left. On my y-axis, I need to go at least up to 2 and down to -2. As best as you can, using those numbers as guidelines, you're going to create the rectangle. Keep in mind, it has to be dotted. And again, anything dotted you can use as not a part of your final graph, but anything that's solid considers itself a part of your graph. So you don't want to put it solid. Okay, once we have the rectangle, we're going to try to make diagonals from one corner to the other and extend them out so you have good guidelines. And again, these need to be dotted. Now we go back to the equation. We have no x-intercepts because the negative was on the x. So it's really the y that we're going to intercept. So this 2 and this -2 exist, and this one's going to open super wide, and we're going to follow those diagonals as asymptotes. At this point, you should pause the video and try this next example by yourself before you play it for me to go over. Okay, so I'm going to start by trying to set it equal to 1. So I'm going to divide everything by a 36. The x squared over 36 is going to stay as is. The 9 goes into 36 4 times, so that's going to get reduced. And then 36 over 36 is 1. So when I look at 36, I'm thinking plus or minus 6. When I look at the 4, I'm thinking plus or minus 2. But keep in mind that your negative is on the y squared. So on my x and y axes, I'm going to go out 6 on the x-axis, and then in the negative direction as well. I'm going to go up 2 and down 2 on my y-axis. I'm using these as guidelines to make a rectangle. Again, make sure it's dotted. We're going to use this rectangle and do the best that we can to make nice straight diagonals. Again, those are dotted as well. Then we're going back to our equation. The negative was on the y squared, so we have no y-intercepts. So we're actually using the x values of 6 and -6 along with the asymptotes that we've created to try to get our hyperbola on paper. There's another type of hyperbola that exists, and if you think about it for a second, we've been talking about ones that look like this and ones that look like this. However, what happens if a hyperbola has a shape that looks something like this in quadrant 1 and 3 or in 2 and 4? This would be created when you have what's called inverse variation. Now, in the past, you guys have done direct variation where you set up a proportion, and when you do that, when one variable goes up, so does the other. When one goes down, so does the other. For example, how many hours a week you work and how much money is in your paycheck. If you work more, you get more money. If you work less, you get less money. That's a direct relationship. We're going to talk about an inverse relationship. And what that means is, as one thing goes up, the other thing goes down. Okay, so if you look at, let's say, for example, this equation over here was xy equals 12. If I set up a table of values for that, if x was 1, y would have to be 12 because 1 times 12 is 12. If x was 2, y would have to be 6 because 2 times 6 is 12. If x was 3, y would have to be 4. If x was 4, y would be 3. If x was 6, y would be 2, and so on and so forth. If you look, your x values are going up, but your y values are going down. And if I were to plot this, 1, 12, 2, 6, 3, 4, 4, 3, 6, 2, etc. Now, don't forget, what could happen here is I could have -1 and -12, -2 and -6, -3 and -4, -4 and -3, -6 and -2, in which case your x values would be going down and your y values would actually be increasing. And if you plotted those points, -1, -12, -2, -6, -3, -4, -4, -3, -6, -2, and so on and so forth, you would get that picture that you're seeing in quadrant 3. So when you have an x times y equals 12, or y equals 12 over x, okay, where this could be any constant number, that's called your constant of variation, you would get what's called an inverse hyperbola. Okay, so where do you see this in real life? Let's say a bunch of people were renting a limo together, and let's say the limo costs $1,000. Let's let x be the number of people in the limo, and let's let y be the cost per person. Okay. If you have one person that wants the limo by themselves, it's going to cost them $1,000. If you have two people sharing the limo, it's going to cost them $500 each. If you have 10 people in the limo, it would cost them $100 each. So if you see this side is increasing where this one is decreasing. The more people in the limo, the less per person it would be. In a situation like this, you might have to restrict your variables and your domain and range, because even though you have a positive times a positive to equal this positive, or technically a negative times a negative to equal the positive, in the context of the problem, you're not going to have a negative number of people or a negative cost. So you would only be having the picture in quadrant 1. You would restrict where your x value would have to be greater than 0 and your y value would have to be greater than 0. Okay, similarly, if I say it takes one person 10 hours to paint a house, then that means it takes 10 man-hours to paint this house. If I have the same house and the following year I hire 2 people to paint the house, it should still be a 10-hour job. It's still 10 man-hours to paint this house. So if 2 people show up, it should only take them 5 hours to paint the house. If 5 people showed up, it should only take them 2 hours to paint the house, still giving them that 10-hour window. And if 10 people showed up, it should only take them 1 hour to paint the house. Okay, it's always got to total that same constant variation. So in this case, your equation would be x times y equals 10. And again, you would never have a negative number of people or a negative number of hours to do this job, so you would only have that picture forming in quadrant 1. Let's read this next example. The staff in the office wants to buy a gift for the boss. Let x equal the number of people contributing to the gift, and let y equal the amount each person will contribute. If they decide to buy a gift that will cost $100, write an equation to represent this, then graph. Why don't you take a minute, write an equation, see if you can come up with some points and sketch the graph, and then play the video once you're done. Okay, so let's say you had one person contributing. Then that one person would have to pay the whole $100. If you had 2 people contributing, they'd be paying $50 each. If you had 5 people contributing, they would be paying $20 each. If you had 10 people, then it would cost $10 per person. So in every case here, your constant should be 100. So looking at what you wrote, if x is the number of people contributing to the gift, and y is how much each person has to contribute, then your equation needs to be x times y equals 100. So when you go over to the graph paper, you can use the points that you've just created. You just have to be really careful on a scale. You really can't go by ones if you want to go out to 100, but we'll probably just, I would say go by like 5s or 10s. So 5, 10, 15, 20, etc. In a case like this, I would do the same thing here, 5, 10, 15, 20. And you could continue, and I'll probably just kind of sketch it. But you have 100 is something crazy up here. You have 2, 50 is something down here. 5, 20 somewhere over here. 10, 10 is somewhere over here. And then if you had 20, you'd be going down to 5. Okay, so you have a situation that looks something like that. Now, even though a positive times a positive is equal to a positive, and this could be a negative times a negative, it doesn't make sense to have negative people or negative money in this context, so we're just going to keep that quadrant 1 sketched. Now, if we really wanted to get technical, money can be decimal form, but if this x value is representing people, you should really only have whole numbers, which would kind of alter our graph again. But right now, we're just trying to get a general overview of what an inverse hyperbola looks like and where you might see one in real life. So for right now, I'd say this is pretty good. I hope everyone is doing well. I miss you guys so much. And hopefully we will see each other soon. If you need anything, please feel free to email me.